Hello, so we are here again for our math learning in calculus. So this time what we will be doing is, let's try to start with an activity. Let's try to start with this activity. We have two columns A and B. What we will be doing is you will be matching the derivative of column A to its corresponding derivatives to column B. So if ever we'll be doing this, if you can recall with all the concepts you have with derivative, so this is basically the basic derivatives, right? So for example, we have number one, so f of f of x is equal to x cubed plus 2x squared plus x. So if ever you'll be searching for its derivative, so x cubed will be 3x squared, this will be 4x, and this will be 1. So it will be 3x squared plus 4x plus 1. So I believe we will match it to letter D. And let's proceed to number two. So this is 3x squared, 2x, and 1. So 3x squared, 2x, and 1. So for number 2, let's match this with letter C. Let's proceed to number 3. So this will be 4x cubed, this will be 9x squared, and 1 will be 0. So that will be 4x cubed plus 9x squared, so that will be matched to letter E. Afterwards, let's proceed to number 4. That is, this will become 4x cubed, this will become 3x squared. So I think you'll agree with me that we will match it to letter A. And for the last one, we have here 9x squared plus 3 and 1 will be 0. So this will be matched to letter B. So what we were doing earlier is basically we solve for the derivatives of column A, and we will be matching it to column B. Now, since we learn most of the concepts in derivative already, especially in algebraic expression, now the question will be, what if we will be doing it backwards? What if you are provided with column B, and for example, you have this 4x cubed plus 3x squared, and you know that this is the derivative of a certain function. So our challenge here now is we need to know what was the original function before we solve the derivative to get this specific derivative of our function or our f prime of x. So on that sense, then that's why we will be talking about anti-differentiation. If you can remember, when we talk about derivative, it's like the derivative or getting its differentiation. So our concept for today will be all about anti-differentiation, or we call it integral, okay? So we call it integral calculus. So maybe the question, maybe you're wondering, what is anti-differentiation? So let me provide you its definition. So it states here that it is the process of finding the antiderivative of a given function. So I know it is quite complicated still to understand. So in layman's term, this is the easier way to understand the meaning and the concept of anti-differentiation. And that is, it is getting its derivative backwards. All right, so we will be solving its derivative, and we will be getting its or we will be doing it backwards. All right, so for example, you have a function, you have a derivative function f of x. So your goal here is to solve for the original function. So that is our goal. So that's the concept of anti-differentiation, wherein we will be getting its derivative, but this time backwards. So how do we do that? So that's the challenge. So that is why we will be guided with some theorems and principles in solving for the anti-differentiation. I just want to clarify, though, that when we talk about anti-differentiation, to not be confused when we associate this to integral, or when we associate this to anti-derivative. Because again, if you can remember, what we were doing last time is we are solving for the derivative. So working backwards, it's anti-derivative or anti-differentiation, or again, the integral of that specific function. Now, let me show you the different notation in writing anti-differentiation. And here, if you can see the symbol, this is the symbol for anti-differentiation, and this is what we call the integral sign. it denotes the operation of our anti-differentiation or antiderivative, and the function f is called the integrand. I'm sorry. So the function f is the derivative of the function you are looking for. So to properly write anti-differentiation, we do it this way. So the integral of f of x, then here there must be dx here, because technically um, if you can remember, when we will be solving for the derivative of a function, we always put it in mind that we have dx, right? So for example, if you can remember, when when you do implicit differentiation, for example, when you solve, so when you have y is equal to x squared, its derivative is actually 2x times the derivative of x. However, in this case though, the derivative of x is just equal to 1, so instead of writing this, we write this as just 2x. So this dx symbol is a representation that this is the derivative of the function we are looking for. So this is how we do it. So this is how we read it, the integral of f of x dx. So again, this is the integral sign. This portion here is the integrand, and this is the derivative symbol. So for this, again, our goal here is we need to solve for the original function before we got the derivative, before we got this answer. So we are looking for the original function, and that is always equal to c. So this is, maybe you're wondering, because if ever you will be scanning over your notes, or whichever it is, or perhaps books, you will be able to see that there are always plus c. Even if you solve for the integral of g of x dx, if ever we'll be solving that, so we are looking for the original function plus c. Why is it so? Because that plus c denotes that um, because the derivative of a constant c is always 0. Let me show you an example for that. For example, we have 2x squared, right? And we have 2x squared plus 1. And we have 2x squared minus 1. And we have 2x squared plus 3. If you notice, everything has 2x squared. However, in this case, the 2x squared is 0. The constant added here is 1, right? And the constant added here is negative 1. And the constant added here is 3. If we solve for its derivative, this is 4x, right? And if we solve for its derivative, it's still 4x. And if we solve for this derivative, it's 4x, because the derivatives of these constant is 0. And the derivative of this one is also 4x. So if you notice, this is our capital F of x. This is the one we are looking for, right? And these things are the, I'm sorry, these derivatives are is the function inside the integral sign. All right, so that's f of x. So this is our 4x. So it's like integral of 4x dx. So again, our goal here is to solve for the original function. But however, if you look at it, technically there are infinite number of functions. Why? Because 2x squared will have a derivative of 4x still. 2x squared plus 1 will also have a derivative of 4x. So instead of us writing all those constants added to 2x squared, we just put it plus c. So technically then, if ever you will be solving integral of 4x dx, we were able to see from here that the original function from that is 2x squared. Then instead of writing all those functions, I mean all those constants, we can just put a representation that is equal to c, because any constant added to that will always be equal to 0 when we get its derivative. So the answer for this is just 2x squared plus c. All right, so that's the concept of anti-differentiation. That's how we write it. So again, I just want to clarify, we read it as the integral of f of x dx. And this is the answer we're looking for. This is the original function prior us getting the derivative, prior us getting this derivative. So that's the concept of anti-differentiation. Well, don't worry, later on with our classes, we will be, or I'll be providing you with some examples in real life. However, we need to master the concepts. We need to master the theorems and rules in anti-differentiation before being immersed with all those real life applications. All right, so without any further ado, let's proceed to the integration rule. So this is the first integration rule. So the integral of dx is equal to x plus c. So how did it happen? So if you look at it, there is no number beside it. There's no variable. It's just dx. But if we basic concept, we will be able to know that there is an imaginary one here, right? So always the integral of 1 dx is just equal to, it's like 1x plus c. All right, so or it's just x plus c. Okay, so this is the first integration rule. Well, let me provide you with some examples, all right? So for you to be able to understand how this first integration rule be applied. So we have here, so the integral of 100 dx. So technically, if ever you will be solving this, so the number beside dx is 100. So what you will be doing here to solve for that is just copy the constant, and dx is just x, then plus c. So that's how you do it. So it's again, integral of 100 is the integral of 100 dx is just equal to 100x plus c. All right, so let me provide you with some another example. Let's have another example for that, which is this. So integral of 3/5 dx. So what you will just be doing is always, since it's just a constant here, you just copy the constant and you put the variable you were using here. So 3/5, since we're using here with x, so 3/5 x plus c. So your answer is this one. So that's how you do, and that's how you apply the integration rule number 1. Again, the integral of dx is just equal to x plus c. So no matter what constant you're using, it will always be in this format. So for example, we have integral of pi dx. We all know that pi is not a variable. Pi is a representation of a specific number. So technically the answer here is copy the constant, put x, then plus c. All right. Another thing, perhaps, if you can remember with our natural logarithm, we have e. All right. So it's a constant approximately equal to point something. So if we will be doing this, we can put e. Since that's constant, put x, and then plus c. So that's how we do that. Always remember, there's always plus c because, again, it's a family of those constants added. Okay, so that's the first integration rule. Let's proceed to the second integration rule, and this is the second one. So this is the most applicable integration rule among them all because everything will be patterned on this. So the integral of x to the power of n dx. So again, this time the expression beside dx is no longer a constant. It is now an expression x to the power of n. So how do we do that? So its integral is just actually, you simply copy x to the power of n, but this time plus 1. If you can remember with differentiation, we are subtracting the exponents by 1. Since we are doing it backwards, we will be adding it by 1. All right, so if previously we are subtracting it by 1 through derivative, this time we will be adding it by 1 through its opposite, through its anti, which is the anti-differentiation or the integral. So n plus 1, and then what you will be doing is to put n plus 1 in the denominator as well. So x to the power of n plus 1 all over n plus 1, and do not forget plus c. All right, so please do not forget plus c. So you just need to follow this pattern and how to solve for examples like this. Well, don't worry, I'll provide you with some examples. And this is our first example. So integral of x to the power of 5 dx. So if we solve for this, it will be x to the power of 5 plus 1 all over 5 plus 1, then plus c, right? And then afterwards, 5 plus 1 is 6. And 5 plus 1 is, of course, 6. So your answer is x to the power of 6 over 6 plus c. Or if you want to write it in another way, it could be 1/6 of x to the power of 6 plus c, right? So it will just be the same concept, okay? So either of the two, there is nothing to be worried about if which format do you wish to apply and how to write fractions, all right? So that's how we apply it, okay? So it's very easy. Now let's proceed to another example on this, which is this. For example, we have this. Oh, so this time we have a rational function. So if ever you will be engaged with this, always, because our format here is always x to the power of n. However, this time it's like 1 over x to the power of n, right? So if you notice, it's on that form. So in this example, what you will be doing every time you'll be encountering irrational function or irrational expression, everyone, what you will be doing is you just need first to put it on top. And of course, if you can remember, if there is a negative exponent on top, you put it in the denominator to make it positive. But since we're doing it backwards, the positive exponent in the denominator, when put on the numerator, then it will be a negative exponent. All right, so please remember that in your loss of exponent. And if you will now be applying the integration rule, I'm sorry, this will be x to the power of negative 3 plus 1 all over negative 3 plus 1. And do not forget plus c. Okay, afterwards, I think you know that negative 3 plus 1 is negative 2. And if you have observed, everyone, the exponent here will always be the denominator here. So yeah, that's just one of the techniques in integration for algebraic functions. So in this one, I believe you'll agree with me that this will be 1 over negative 2x to the power of 2. Our negative exponent here will be placed in the denominator and it will be positive, and that's what will happen. So this answer is correct. However, to write this formally, we can just put negative 1 over 2x squared plus c. This could be an answer. Or if you wish to, we can put it negative 1 half x. No, I'm sorry. It's actually wrong. So, well, basically, it's just between the two of them. So this one, this could be a correct answer, or this other one as well. Okay, because remember, the x squared is in in our denominator. So that's how we have our answer for the integral of 1 over x cubed dx. So the guide here is just to follow the format in our integration rules. All right, so we are done with the first two integration rules. So this time, let's proceed to the third integration rule. The third integration rule is this. So for example, you have like integral of a constant times f of x dx. So you can just pull out our constant. So the constant can be pulled out and placed outside of the integral symbol. So it's like a times f of x dx. So please take note that this is only applicable when, okay, please listen. This is only applicable when our constant is beside a specific expression. When a constant um, is beside with x or any variable that you are solving. However, if constant is alone, then you can apply the first integration rule. All right, so let's proceed to some example. We have, we have this. So integral of 6 square root of x dx. So if ever we'll be simplifying this will be 6 integral of square root of x dx. All right. Now, this time, if you notice, it's square root of x. And it's quite difficult to solve for its integration. So that is why always put it in mind, if we have rational and radical, we need to transform it to its exponential form. Square root of x, if you can remember, is just equal to x to the power of 1/2, right? Irradical symbols can be expressed into expression with fractional exponents. So we have square root of x, so that will be x to the power of 1/2 dx. So if you solve this one, we can apply the previous theorem. So this will be 6 times x to the power of 1/2 plus 1 all over 1/2 plus 1. And again, do not forget c. Okay, so after that, this will be 1/2 plus 1, I believe it's 3/2. All right, and so this will then be also 3/2. Okay, and so what we will be doing afterwards, we can continue here. Okay, so our 3/2 here could be reciprocated, right? Because it is a complex fraction. So it's just like 6 times x to the power of 3/2 times 2/3, right? All right, then plus c. And if you check on it, it's multiplication in everything. So you can cancel 3. What's left is 2. So that will be 4x to the power of 3/2 plus c. All right. So this could be your final answer. Or if you wish to transform this back to radical symbol, so this will be 4 then square root of x cubed plus c. And if you notice, there is more in it, right? X cubed. So this will be 4. We can pull out because x cubed has x squared times x, and square root of x squared is just x. So we can have 4x square root of x plus c. So you can have this answer or you can have this one. No worries on that. All right, so that's how we apply this third integration rule. Okay, let's proceed to the next one. The next example for this is this one. So it's integral of 1/3 x cubed dx. So the same rule on this, we can pull out the constant 1/3. So that will be x cubed dx. And if you notice, this is easy, right? I'm applying the previous integration rule, so we can have 1/3 times x to the power of 3 plus 1 all over 3 plus 1, again, plus c, do not forget. So we multiply, so this will be x to the power of 4 over 4, and we have plus c. So what will happen will be x to the power of 4 all over 12 plus c. So this could be your final answer. Or if you wish to, we can write it as 112 x to the power of 4 plus c, either of the two. Okay, so no problem any of these two notation. Okay, so that's it for this theorem. Um, Let's proceed to the last theorem, I believe so. So integral of f of x plus minus g of x dx. So the purpose here is that we can have plus or minus, but not together, okay? So this is just a shortcut way of writing it. So it is just like we can distribute. So we can distribute the integral to f of x. So it's integral f of x dx, then plus minus integral g of x dx. So that's how we do it. So let me provide you with some examples. And this is our first example, everyone. So integral of 12x squared plus 4x dx. So how do we apply this? So this will be integral of 12x squared dx. We distribute the integral symbol plus integral of 4x dx. Well, please put it in mind that when you have an integral symbol, always there is a dx here. Okay, so do not forget that. So I think we can apply the previous theorem here. So this will be integral of 12 integral of x squared dx. And the other one will be 4 integral of x dx. So if we solve this one using the second rule, this will be 12 times x to the power of 2 plus 1 over 2 plus 1, right? Then plus 4 times x to the power, so the exponent here is 1. So I think you'll agree with me that that will be 1 plus 1. So that will be over 1 plus 1. And do not forget plus c. So if you solve this one, this will be 12 times x cubed over 2 plus 1 is 3 plus 4. 1 plus 1 is 2 over 2 plus c. I think we can cancel some factors here. We can cancel 3 by 12. That will be 4x cubed. Plus, we can cancel 2 by 4. What's left is 2x squared. And again, do not forget c. And this is the integral of 12x squared plus 4x dx. So that's how you write it. So as easy as that. All right, so just apply all those integration rules provided. All right, so let's proceed to the last one, to the last example, which is this integral of t times 3t minus 6 dt. So this time we're using a different variable, right? So since we're using the variable t, so it's no longer dx, it's now dt. So be flexible enough in treating these variables provided with you. Now, if you notice, there is a multiplication symbol, right? If in differentiation, there is like the product rule and the quotient rule, I just want to tell you for integration rule, there is none, okay? So there is no integration rule for multiplication and substitution. So what you will be doing is you just need to simplify first before proceeding to integration symbol. Okay, so here, let's go ahead and simplify this one. So perhaps we can distribute t to every expression inside. So this will be 3t squared, right? Then minus 6t, then dt, right? So it's like, yeah, we can just distribute it. Then afterwards, we can apply this theorem flash on screen. So this will be integral of 3d t squared dt minus integral of 6t dt. So earlier that was plus, so this time it is minus. So we can apply the one with a theorem earlier. So this will be 3 integral of t squared dt minus 6 integral of t dt. Then afterwards, we can apply the second theorem. So this will be t squared plus 1 over 2 plus 1 minus 6. And again, our t here has an imaginary exponent 1. So this will be t to the power of 1 plus 1 all over 1 plus 1. Then again, do not forget plus c. Okay, always do not forget plus c. All right, so to continue, we have here this 2 plus 1 is 3 over 3 minus 6 times t squared over 2, and we have plus c. So if you can observe, we can cancel some expressions, right? We can cancel 3 and 3, we can cancel 2, and what's left with 6 is 3, right? So what the answer this time is t cubed minus 3 t squared plus c. So this is your final answer when you solve the integral of t times 3t minus 6dt. All right, so basically that's it for today. Thank you so much for listening, and God bless.